everyone, welcome to another class of this fundamentals of particle and fluid solid processing. Last day we have seen drag force, the concept of drag and the concept of boundary layer. So, I mentioned that these concepts possibly will be much more clarified if we look at some problems, and associated theory we will be looking into this class as well as a couple of forthcoming classes. So, we focus again back to the flow around emerged bodies, and let us say a problem statement says an airplane is dropping food packets one by one over a village for under a relief program, and assume that the food packets weighing 60 kg each are descending vertically down at a terminal velocity of 42 meter per second. The food packets are squared in shape and each size measuring 0.7 meter. So, calculate the drag coefficient of the box, or the drag coefficient that is there on the box. So, how do we solve such problem? Now, there first of all we assimilate that what are the informations that are given and what the things that we should look for. Okay. So, here although there is bit of preamble is there that the airplane is dropping food packets and a relief package, but essential thing is that one square sized packet is coming down vertically with a certain velocity. The box weight is known. So, the cross sectional area of the box is known. So, what is the drag force or the drag coefficient rather here? Okay. So, we have seen that before I go into the problem, here is one term that you are possibly wondering, or if you have forgotten, this terminal velocity of 42 meter per second. Now, during the earlier classes I mentioned when I mentioned about the Stokes law, or if you remember the Stokes law, you can possibly remember that's terminal velocity. So, terminal velocity is a velocity, constant velocity, when a particle or object attains when it flows through a pool of liquid or a pool of fluid. Okay. So, what happens when a particle is dropped in a pool of liquid? It velocity accelerates, it accelerates certain velocity to a velocity, and after a certain time what happens, the forces acting on it and the gravitational force, all the forces balances, and then the particle does not accelerate anymore, it then falls through a constant velocity. That velocity is called the terminal velocity. So, it is a constant velocity. Okay. So, that is what the information is given here. It is falling, let us say, at a terminal velocity. So, you can neglect the initial part when it accelerates, and after attaining the velocity we have to calculate what is the drag on it, okay, to simplify the problem. So, the drag force that is given here, or we know, is that Fd is the drag force, where this is equated with these expressions that we have seen earlier, okay, where Cd is the drag coefficient, rho is the density, A is the cross sectional area on which the drag force is acting, and V is the velocity through which or with which it is traveling. Okay. Now, as given in this case, the object is falling through the atmospheric air. Okay. The typically air density is known. That information is explicitly not mentioned here, but we should remember this value at typical ambient condition is 1.2 kg per meter cube, and the terminal velocity V is given. Okay. The area upon which drag acts is the cross sectional area of the box. For that, the area calculation of the cross sectional box, we know its side, that is 0.7 meter. So, we know the cross sectional area, And since the box is dropped from the plane, it can be considered, and in fact it is mentioned that the box is settling through the air at a terminal velocity. So, which means there its weight and the drag force balances, okay, and that is why there is no acceleration of the object or the that food packet or the parcel. So, this weight is here, that is what given. Okay. The drag force, we have this expression which is equals to some known values that is given in the problem already. Okay. Now, here rho is known, cross sectional area is known, V is known, we have to find out what is CD. This is as simple as this looks like. So, which means this is our equated form, that this drag force is equals to mg. So, we calculate, find out what is CD based on the numerical values or numerical parameters that are given in the problem, because all other parameter values are given in the problem. I hope this is clear. Okay. Let me again go back to the same problem. So, the problem was, there was a square shaped object falling through air of known dimension, known weight. Okay. We have to calculate what is the drag coefficient of the box, the velocity at which it is falling, the constant velocity, that is also given. So, in that case, since it is the terminal velocity, the drag force is equals to the weight of the box, okay, and that drag force expression contains CD. In there, CD, rho, A and V square, except CD, all these parameters are given. This is equated with the weight, which is mg, and we find what is CD. So, this is the drag coefficient of the box. Okay. Now, we move on to the next problem. The problem is that a cylinder, now instead of a square shaped object, we have a cylinder which is 4 meter in diameter and 20 meter long, is dropped in seawater and settling at a velocity 1.3 meter per second. So, find the drag on it. Okay. Now, this problem statement is relatively broader, or it can be perceived in different ways, that what is the several questions can be asked. In fact, you should ask that in which orientation it is dropped, how it is traveling, and etc. So, based on that, those questions or those information, the solution will differ for such problem. Okay. Now, here the drag coefficient for Reynolds number greater than 10 to the power 5 is mentioned, that can be taken as a constant value, which is 0.75. The density of water is given 1035 kg per meter cube, and kinematic viscosity is 0.015 Stokes. Okay. So, the here question is what is the drag exerted on it, where the drag coefficient value is given if the Reynolds number is more than 10 to the power 5. Okay. Such information is given. So, typically you can understand the Reynolds number will possibly greater than that, but still you need to calculate and show that the Reynolds number is certainly more than 10 to the power 5, and so the drag coefficient CD value you have taken as 0.75 and have done the rest of the calculations. So, here we have to calculate what is the drag force or the FT value. Okay. So, here the diameter of the cylinder, length, velocity, density of water, kinematic viscosity, all these informations are given, all the information are given here. The drag coefficient is strongly influenced by the Reynolds number, because with the Reynolds number drag coefficient correlations are given. Okay. So, we have to find out at first the Reynolds number and check how much it is. We see for this particular problem the Reynolds number is in the magnitude of 10 to the power 6, which is much higher than the 10 to the power 5. So, we can consider the drag coefficient CD value as 0.75, that is mentioned in the information that is given in the problem. Okay. So, we have to now calculate what is the drag force, and for that the drag, the area on which it is acting, Okay. Now, here the area is pi L d, or if d is 2 r, you can consider, so 2 pi r h, which is the surface area. Okay. So, drag is acting on this. So, it is the, if we consider this is the screen drag. So, now you can understand that since we have calculated in this way, how the particle is flowing. Okay. So, it is a kind of a, let us say the submarine is going through the water, okay, with a velocity of 1.3 meter per second or something like that. So, then it has its surface area on which the drag force is acting. So, accordingly the area is calculated and the drag force is calculated with the, which is around this value 1.6 into 10 to the power 1, 2, 3, 4, 5 for 10 to the power 5 Newton. Okay. So, the first problem, the drag force was given in terms of weight, we had to calculate what was CD. In the second problem, the CD values was given and we had to find out what is FD, or the drag force. Okay. Now, we move on to the third problem. So, here what we see, that a problem says that a shell and tube type heat exchanger which houses a tube bundle around 20 tubes in number in a process plant. We use such shell and type heat exchanger in chemical process plants. So, where these tubes have a outer diameter that is cylindrical in shape is of 9.3 millimeter, and the pitch, that is the center to center distance during the stacking of this tubes. So, here if you look at this picture, so this is the tubes, or these are the tubes that are stacked in this way. Okay. So, this is the outer diameter D and this is the P. So, center to center distance between the two tubes. Okay. That is also mentioned here. Now, on the shell side, that means through these spaces, this one of the shaded space. So, one portion of this is marked here. So, similarly, there is in between tubes the space, we call it shell side. So, there coolant water is flowing. Okay. So, in that case, the question is calculate the friction drag exerted over a single tube. When the water flows like this perpendicular to the depth of this slide or the monitor, you can see what is the friction drag exerted on one tube. Okay. So, here the properties of water are given, which is the density is given, the coolant liquid, it is not water, it is a coolant liquid here, and here the viscosity is also mentioned, and it flows through the gaps with a velocity 5 meter per second. So, what is the drag on this one? So, again similar to the second problem that we have just solved, here we again have to calculate that what is the Reynolds number, because we have to find out at first what is the CD value. If you remember, the drag force is equals to half CD rho A V square. Now, to calculate the drag force, we need to know what is CD, and CD should be calculated based on the Reynolds number. Based on the Reynolds number range, we find appropriate correlations for the CD or use that, and then get the overall drag forces if all other parameters on the right hand side are known. Okay. Now, to calculate the Reynolds number here for this liquid that is flowing through the shell side, okay, what would be the D diameter or the equivalent diameter, because flow through tube we can easily understand it is the diameter of the tube. Now, here the flow is happening over the tube and through such gaps. So, basically we have to find out what is the hydraulic diameter or the equivalent diameter. Now, in this case few additional information are given to help you. One is that definitely this information is required, that the length of the tube is 4 meter long. The relative roughness of the tube surface is 5 into 10 to the power minus 4. Okay. And this equation for hydraulic diameter is directly given. Now, this depends on the diameter of the tube as well as the pitch, that is the center to center difference between the tube. So, for this kind of rectangular pitch, this is the equation for the hydraulic diameter, which can be derived. You can derive, but for the sake of simplicity here we have directly shown. So, if the orientation, let us say, is like a triangular kind of a thing, the pitch is like triangular, the available area is triangular, this hydraulic diameter expression would be different. So, this expression is supposed to be derived by, but let us say here it is given, and then this hydraulic diameter will be used to calculate the Reynolds number to understand or to have the CD value. Okay. So, here the Reynolds number expressions dV rho by mu. Okay. Here this velocity is known, density is known, viscosity is known, the dH would be fine, we will get it from this expression. Okay, for this internal outer diameter of the tube and the pitch dimension. Based on that, we find out at first what is the hydraulic diameter. Once that is done, we find out that what is the Reynolds number. Okay. And now, we see this is a kind of a turbulent condition. Okay. Now, with this flow type, we can use Moody's chart, if you remember that, which has the friction factor versus the Reynolds number for different surface roughness tubes. Okay. There, if we find out the value using that chart, any classical textbook, you can find out, any classical fluid mechanics textbook, you can find out that kind of chart, and we will see that the Darcy friction factor value is this one. Okay. So, the fanning friction factor is 1/4 of that value. Okay. And then this fanning friction factor is basically the drag coefficient of the friction. Okay. So, now the FD friction, or the question was here, if you look at again, the question was calculate the friction drag exerted over a single tube. Okay. So, which means we need the coefficient of friction for the drag in this case, which is that we have got from the Moody's chart, and we find out for a single tube like we did for the second problem. 2 pi RH is the available area on which drag force is being exerted, and we replace now the numerical values to get the drag force, the screen drag force for the friction drag force over a single tube. So, this is how we calculate drag force, the drag coefficient, and related question we have to solve. Now, let us quickly have a look at a different problem. So, the problem says that a thin flat plate is placed parallel to a 6 meter per second stream of water at 20 degrees centigrade. At what distance x from the leading edge will the boundary layer thickness be of 2.54 centimeter or 1 inch? So, this is the problem statement. Now, you can understand that this problem is, we came from the drag calculations or the drag coefficient calculations to boundary layer calculations. Okay. So, this is one of the simple problems to understand that how boundary layers can be calculated. Although I have not shown you in details that different correlations available or different drag coefficients available for different shapes, sizes, because those are typically covered in fluid mechanics classes. And the kinematic viscosity of water at 20 degree centigrade is also mentioned, or these are typically given in form of a table or any appendix of any textbook. You can have this value collected from there. So, the point is, a thin flat plate is placed parallel to a 6 meter per second stream of water at 20 degree centigrade, at which distance there will, from the leading edge, there will be the boundary layer thickness of 1 inch, which means you have a flat plate, the water is flowing over it, okay, and from the leading edge to how much distance there will be a boundary layer thickness of 1 inch. This is the question. Okay. So, how do we solve this? There are several correlations available to find out. If we say the thickness of the boundary layers as delta and the distance from the leading edge is x at a certain point where the thickness is delta, then delta by x is equals to some constant multiplied by the Reynolds number to the power some factor, okay, some coefficient. Okay. So, this is the typical relation that I have mentioned earlier. This is the typical relation that there with the delta versus RE. So, which means for this problem you have to calculate what is RE. Now, that distance is, so for a particular distance what would be the RE in that case. Okay. So, how do we approach this problem? So, first of all we assume, since the Reynolds number is not known, we assume that the flow is laminar. Okay. So, the steps are that since here those informations are not given, you can assume a flow condition, you solve it, you solve the delta for that particular condition, and then you recalculate or calculate back that whether the Reynolds number condition is satisfied or not. For example, here we at first take that this is a laminar flow condition. Okay. Now, for laminar flow condition, del by x is equals to 5 by Reynolds number to the power half. This is the correlation. Okay. If we put these values now here, okay, that delta is 2.54 centimeter, which is 2.54 divided by 100 meter. X is unknown, okay. U value is given here as 6 meter per second. Nu, which is the kinematic viscosity, the value is straightforwardly given here. Okay. So, if we replace this value, we calculate for x, we have a value 155 meter, which means it requires, if we assume laminar flow condition, which requires 155 meter of a long plate, which is a kind of absurd or illogical. So, what should be done here? So, which means we calculate back now whether our Reynolds number calculations was satisfied or not, whether our assumptions of Reynolds number in the laminar zone was right or wrong. So, we calculate the Reynolds number based on this x. So, here u was 6 meter per second, x is this value and kinematic viscosity is already given. If we place that, we see that this value comes out in the range of 10 to the power 8 or 10 to the power 9. Okay. Which means that it is definitely not a laminar flow conditions, because the laminar flow condition prevails on the flat plate till the value of 10 to the power 5, okay, the flow over a flat plate in such condition. So, in this case this condition is not satisfied. So, that is why such illogical results we are having. Fine. So, we go for the turbulent condition. The relation for the turbulent condition is given as this expression. Okay. So, here again similar to that previous calculation, we calculate that what is the x by this expression. So, here the expression was Reynolds number to the power half, here Reynolds number to the power 1 by 7 at the denominator. Okay. By doing this, we replace the numerical values, we find out what is x, and we see that x is now around 1 point, numerically equals to 1.6 meter, which is logical, okay, and it makes sense. We calculate back the Reynolds number based on this x, and we see that Reynolds number in this case is around again 10 to the power 7 in the magnitude 9.6 into the power 6. So, which is definitely greater than 10 to the power 6, okay, and this is definitely a laminar turbulent condition, which we have calculated rightly. So, the mismatch between the theory and the calculation is eliminated by this assumption. Fine. So, which means what we have covered today is that couple of calculations related to drag force and the drag coefficient. So, the first problem was how to calculate the drag coefficient. Second, third problem was related to the calculation of the drag force, and the last problem that we have solved is related with the boundary layer calculations. Okay. So, in the next class we will be seeing more details about this. Till then, thank you for your attention.